The polar regions are changing dramatically. This is due to climate change. And we need to monitor and understand these changes, but it's very difficult to go there and measure. Sending people there is extremely difficult, and you can only measure in a number of places. CRISTAL will really give us a full map of the changes in the cryosphere in the most inhospitable regions of the world.
It will be the first high-resolution operational radar altimeter mission for the cryosphere.
Well, what's really fascinating about CRISTAL is that from several hundred kilometers up in the sky, we will be able to measure differences in elevation of the order of centimeters.
CRISTAL stands for Copernicus Polar Ice and Snow Topography Altimeter. So it's a mission of the European Copernicus program. It is basically ESA's new ice mission, and CRISTAL will focus on the cryosphere, the domain of ice and snow.
The cryosphere is the world of ice, and it plays a crucial role in climate on our planet. Also, it harbors a diverse ecosystem. Over the last few decades, we've seen the cryosphere changing dramatically, in particular shrinking a lot. Ice is melting on ice sheets and glaciers. The snow cover is reducing everywhere, and sea ice is also disappearing. It means that the extent is reducing, and where we still have got sea ice is getting thinner. There's also the permafrost, the frozen soil at high latitude, which is thawing, and when it thaws, it releases methane, which is a greenhouse gas, so it makes global temperature rise even more. I am Paolo Cipollini. I'm the mission scientist for CRISTAL and also for another mission of the Copernicus constellation, Sentinel-3 Next Generation Optical. How much ice are we losing? To put this into perspective, since 1994, on our planet, we've lost over 28 trillion tons of ice due to melting. 28 trillion tons of ice. This corresponds to an average of 1 trillion ton every year. In case you're wondering how much is 1 trillion ton, well, it is a giant cube of ice with a side of 10 kilometers that melts every year. And this melting is accelerating. We know from the measurements that Greenland, for instance, and glaciers all around the world are now losing ice even faster than in the past. And that's another thing that we see. Every passing year, we see colossal icebergs rupturing from Antarctica, from the Antarctic shelves, much like a recent one, which was as large as Greater London, 150 meters thick. And we see more and more big icebergs rupturing from Antarctica. This general loss of ice that we see is very serious because it has an effect on several of the fundamental cycles on our planet, the cycles by which our planet works. And first, the water cycle. The huge ice sheets that we have in Antarctica and in Greenland, they hold the largest quantity of fresh water on the planet. When Greenland, Antarctica, and the glaciers melt, they release this water to the ocean, which causes sea level to rise. And sea level rise is a big problem because it will affect billions of people that are living around the coast. Activities will have to be relocated. We might have to move infrastructure. Melting of ice sheets today represents one of the largest uncertainties in the prediction of future sea level rise, which means we don't know how much is melting well enough to improve our predictions, and we would like to know better. Improving the measurements means that we can improve the prediction and prepare better for this big impact of climate change. Melting of ice also affects another cycle on our planet, the energy cycle. That means how energy from the sun is absorbed and redistributed around our planet. And sea ice has got a very important, crucial role here because it's bright. It will normally reflect a lot of the energy back to space. But when it melts, the ocean exposed, it's darker. So the darker waters will absorb more heat, and this means further melting. We call it a positive climate feedback, although not positive in the traditional sense of the word. To improve our measurements of sea ice, we also need to measure from space the depth of the snow that sits on top of the ice. We currently do not have good data on this. CRISTAL will observe and measure all the components of the cryosphere. The thickness of sea ice has no depth, but it will also measure the height of glaciers, of the ice caps and the ice sheets, and it will detect icebergs and estimate their volume.
Measuring iceberg volume is also important to understand how much fresh water is being carried away from our poles to other regions in the oceans. When they eventually melt, they cool and freshen the ocean, affecting ocean currents. The ability to detect icebergs is also a valuable information for maritime traffic. Icebergs still present a significant hazard to shipping, and detecting them helps with navigating safely in the Arctic Ocean, which is becoming busier and busier as the sea ice diminishes. I'm Christophe Gantois. I'm the CRISTAL project manager. Basically, I'm the one with the glue, making sure that everybody works well together, that we don't miss any points, and that the project remains on track. CRISTAL is what we call an operational mission. Operational means that it is designed to make long-term sustained observations that are essential for many applications and for climate science.
The radar altimeter on board CRISTAL, called IRIS, has two very distinctive technical features. First, it measures using two different radar bands. From the difference in the two measurements, it can crucially measure the snow depth, because one signal is mostly reflected from the top of the snow layer, and the other penetrates the snow down to the ice layer. IRIS also has two receiving antennas. Conventional altimeters with a single antenna only measure at nadir, which means on the ground track immediately under the satellite, under the vertical of the instrument. IRIS will exploit these two antennas and the slight difference in the echoes that you get from the two antennas to extend the measurements on the sides of the track. This is a technique that we call interferometry, and it has been pioneered by CRISTAL.
CRISTAL builds on the long heritage of CryoSat, which is a previous ESA Earth Explorer mission dedicated to the cryosphere. CryoSat was launched in 2010. Initially designed for 3.5 years of operations, this research-driven mission is still providing excellent data after 13 years in orbit. CRISTAL will continue from CryoSat's observations and take them to the next level by providing an operational capability of systematic, long-term, high-resolution monitoring of the polar regions.
CRISTAL will carry two instruments, a radar altimeter and a microwave radiometer. A radar altimeter is a radar that measures heights. And as an observation technique, radar altimeter is very simple. The satellite transmits a radar pulse down, that gets to the surface, bounces back, and by measuring the time that it takes to go down and bouncing back, we measure distance. Let me illustrate it with a little probe. Imagine that you want to measure the altitude of a river, of the surface of a river, from a bridge above it. You know the altitude of the bridge, and then from the top of the bridge, you cast a long measuring tape until you reach the surface of the water. And by taking the difference between the altitude of the bridge and what you've measured, you compute the level of the river. So the radar pulses from my satellite are the equivalent of this measuring tape. The other instrument on board is the microwave radiometer. And the microwave radiometer helps to correct the altimeter measurements for the effects of the atmosphere, and so it makes the altimeter measurements more accurate. And it will also help us to recognize different types of ice and snow. Europe has played a significant role in the development and operational implementation of radar altimeters on satellites since the 1980s. ESA had the first Earth observation environment satellite, ERS-1, launched in 1991 with an altimeter on board, as the following ERS-2 and ENVISAT. And more recently, ESA has developed radar altimeter for the operational Copernicus missions, Sentinel-3 and Sentinel-6. Those are primarily designed for ocean observations. CRISTAL will be the first operational radar altimeter designed for a cryosphere.
CRISTAL's IRIS radar has also several technological enhancements compared to other missions. One to mention is the bandwidth of the radar, which has been increased with respect to Cryosat. In practice, this means that CRISTAL is able to measure tiny variations in height even more accurately than Cryosat. Imagine trying to take a picture with your mobile phone from an altitude of 700 kilometers, and this while you're moving at the speed of 7 kilometers per second, which is about 70 times the speed of a Formula 1 car. In CRISTAL case, we do not take visual pictures, but we send radar pulses with an emitting power of 10 watts, which is far less than a conventional light bulb. And still, with this limited power and ground processing, we can measure heights with a precision of the order of centimeters. Another important feature of the IRIS instrument is that by clever processing of many subsequent radar echoes from a location, we can achieve a sharper resolution in the direction of flight. You can make the analogy by using the burst picture mode on your mobile phone. This one takes multiple photos of the same object and combines them into a sharper picture. And this is what we do when we apply our high-resolution mode. This helps to detect small leads of open water between the sea ice flows, which makes the measurement of sea ice thickness much more accurate. Finally, the instrument will have a special mode that allows to better follow the profile of steep glaciers, so that the changes of those glaciers with time can be reliably monitored. It is a mission of 2 satellites, CRISTAL A and CRISTAL B. Each of these satellites is designed for as a minimum 7.5 years and can work up to 12 years. We will launch them in sequence so that we can ensure monitoring of our cryosphere for at least 15 up to more than 20 to 24 years. Since the CRISTAL mission is dedicated to observing the polar regions, it will fly in what we call a high inclination orbit. This orbit allows us to cover almost completely the poles of the Earth and will extend our monitoring capabilities over these areas. More than 50 companies from 19 countries all over Europe are involved in building the satellite. It is a consortium with large heritage in altimetry missions and having a large collaboration experience. For instance, some of these companies have worked together to build Cryosat-2 and Sentinel-6. This consortium is led by Airbus in Friedrichshafen in Germany, and the IRIS instrument is built by Thales in Toulouse, France. It's a great collaboration of European companies using state-of-the-art technology to build the Altimeter IRIS and a satellite platform. You have to imagine that all over Europe, at this moment, hundreds of people are working on the design and the building of these satellites, in addition to a team of more than 30 people at ESA. We also have a welcome partnership with NASA and EUMETSAT, who both contribute to the mission. NASA will be providing the microwave radiometer, which is our second instrument on the satellite. It is built by JPL in California, and EUMETSAT will be responsible for processing CRISTAL data over the oceans. The Copernicus missions are really a masterpiece of European cooperation in space. Every day, our satellites will take the pulse of our planet, measuring vital parameters of our surroundings. And all these data are open and available to everyone.
We've seen that the cryosphere is so important for our planet and climate in particular. But it's very difficult to go there and measure. Sending people there is extremely difficult, and you can only measure in a number of places. CRISTAL will really give us a full map of the changes in the cryosphere in the most inhospitable regions of the world.
In doing so, it will be the first high-resolution operational radar altimeter mission for the cryosphere. CRISTAL will allow us to monitor the polar regions like never before. This in combination with 2 other future Copernicus missions, SIMMER and ROSEL, which will make complementary measurements to CRISTAL. The first CRISTAL satellite, CRISTAL A, should be ready for launch in the second half of 2027. Then, a few years later, we will launch CRISTAL B so that we can ensure long time span of observations entering into the 2040s.